So, up to this point, in the normal distribution, we didn't really talk about normal PDF, and that's because really that's just used for graphing. You're not going to use that guys at all. All right, so just ignore the normal PDF. The normal CDF is what you were finding. You knew a lower bound and upper bound, and the mean and standard deviation, and that gave you a probability. Okay? Today what we're going to look at is this inverse norm on the calculator. And what this is for is, if we know the mean and if we know the standard deviation, we can find the probability, we can find the score that has a certain percent of the data below it. Okay? So for example, if I wanted to find, say, the probability that if the mean, let's say, is 25, and let's say the standard deviation is 3, okay? Let's say that I wanted the probability that x is less than some value k to equal, let's say, 0.6. Okay? And we want to find k. Now, what's happening here is, first of all, I want a particular value of x. That's what we're looking for. What is the value of x where the probability that we're less than x will be 60%? Okay? Now, what do I know about that value, first of all? Huh?
How are you supposed to know anything about x? Because it's in the problem.
Well, think about it. Think about it. Think about what you do know in the problem.
If x is greater than k, then it's 0.4.
Okay. If x were greater than k, if I wanted the probability that x is greater than k, it would be 0.4. Okay. What else can we tell here? The probability is 0.6. So where is k going to be?
Higher than the median?
What?
Higher than the median.
Higher than the mean. Okay. Yeah, if our probability, and in normal distribution, mean, median, mode are all the same thing. So, if I were to sketch this really quickly here, if I sketch my bell curve, and here's my mean at 25, okay, the probability being 0.6 means that it's going to be here and below, okay? So that's the 0.6. And k is going to be this value right here. Okay? So in order to find that value of k, we're using a new function on our calculator we haven't used before, and that is the inverse norm. Okay? So inverse norm and you'll notice up here, your calculator typically gives you a little menu. If you don't have the menu, you have to plug it in with the probability first, then mu and sigma. Okay? So notice both normal ones, you end with mu and sigma. Normal CDF, you have lower bound, upper bound. Inverse norm, it's the probability, then mu and sigma.
What's mu is standard deviation?
No, mu is the mean.
Oh, okay. So you do probability, mean, and then standard deviation?
Yes. So I would put in inverse norm 0.6, 25, and 3.
Wait, why is the probability the same as area?
Because it actually has to do with how your calculator is finding that probability. The probability is actually defined as the area underneath the bell curve.
Oh, okay.
In fact, we're going to look at this later on in the year when we get to integration. What your calculator is actually doing is it's using the equation of the bell curve and it's taking the integral from negative infinity up to k. Or actually I should say it's not doing that with this, it's doing kind of the reverse process. For the normal CDF, it's finding the integral from your lower bound to your upper bound. Okay? So that's why it's area under a curve.
Okay, thank you.
Okay.
So, in this problem, K. 25.8.
What'd you get?
25.8.
25.8?
But 3 significant figures.
So 25.8%. Okay? Or not percent, just 25.8.
And that's K?
And that's our value of k. Now, make sure that your answer makes sense. If k were at 28, then the percentage would be 84, right? About. Okay, because that's one standard deviation above. If it were at 25, the percentage would be 50%. So I know I'm between 25 and 28. That's where those general percentages that we looked at are very, very helpful to make sure that these answers make sense.
So what is
K is a score. It's a point on the distribution. So what if this were I don't know what this could be. Whatever this was in the situation, if I wanted the value, like let's say let's say this was the average number of cars sold by somebody in a month, okay, car salesman. So he sold an average of 25 cars a month with a standard deviation of 3, okay? Well, if we wanted to figure out how many cars does he have at least a 60% chance of selling, okay, well, that'd be 25.8 cars. So 60% of the time, he's going to sell probably 26 cars. That's what we're saying here. Okay? It's just it's a value of X in the situation. Okay? Let's work through a couple of examples using this, and actually we'll also look at how we can use the standard normal distribution along with this when we have cases that we don't know the mean or the standard deviation. Okay? But let's do a couple of these here first, okay?
Question?
Yes.
Do you use the normal CDF to find the probability, which you then plug into the inverse?
Not typically. The only time we might, well, no, because if you are able to use normal CDF, then you know what the values are. Okay? So, all right, let's take a look at this. All right, this is notation that you guys should be able to read and understand. X is distributed normally. The 38.7 is the mean. Okay, so mu is 38.7. And what is our standard deviation here? 8.2. 8.2, okay? Remember, when you're told X is distributed normally, it's mean and variance.
Right.
So you got to square root it. And usually we write it as S squared rather than, but sometimes we don't, so you got to remember. Okay? So now, if I were drawing this with to illustrate the probability here, Okay? I want x to be less than k, and that probability to be 0.9. All right, so it's going to be somewhere up here. This is going to be k, and that's the area I'm finding. That, or I'm sorry, that's not the area I'm finding. That is 0.9, or 90%. Okay? So if I wanted to find k, I'd be using inverse norm with a 0.9, 38.7, and 8.2. And inverse norm is right in there, right below normal CDF. Okay, so you've probably seen it already. What do we get when we do this? Is 40 what? 49.2. Okay, let's make sure that makes sense. If I have 38.7 plus 8.2, that's 46.9. Okay, that would be the 84% line, right? So it makes sense that this is a little bit higher than that because we want 90%. Okay? Yes? All right, the second one, we've got the probability that x is greater than k is 0.8. Okay, so yeah, this is one you got to be a little careful with because, you know, here, this area above k is 0.8. However, inverse norm, what area does it always take? It always takes the area below, okay? So you need to identify, like Anna did, that this is 0.2, okay? So we are doing, in this case, inverse norm with 0.2, 38.7, and 8.2. Okay? 31.8. And that makes sense. That's a little less than 1 standard deviation below the mean, which makes sense because it's only 80%, not 84.
So we take the inverse norm of these, but what were you saying about 8.2 squared, like redshift squared?
Okay. Remember this, when you have x distributed normally, it gives you the mean and it gives you the variance, not the standard deviation. So that's why it's written as 8.2 squared. That's your variance. So the standard deviation is just 8.2. All right, so let's look at another example here real quickly. This is kind of what like the AP exams and stuff do whenever they're giving out 5s, 4s, 3s, 2s, and 1s. Okay, they have a certain percentage basically that should get 5s. Okay, and it's not exactly like this, but kind of the same. This is how they adjust for if the test that year was a little bit easier than previous years or something like that. It's just not the same score every year that gets you a 5. But here what we have is we're trying to kind of normalize the grades. So this guy, the teacher said that the average score was a 46 and the standard deviation was 25. So his scores were all over the place. Okay? The mu is 46, standard deviation is 25. Now, he wants to give an A to the top 7%.
I mean, probability is the x is greater than point.
0.07.
So
0.93.
So the probability x is greater than k equals 0.07. So yeah, what we need to use is the probability x is less than k will equal 0.93. Okay? So assuming that this is normally distributed, find the lowest score that would achieve an A. Alright, so what is that k? The k value is going to be our score that would get us an A.
Does this include, like, is it greater than, like, less than or equal to, or is it just less than?
Well, that's the thing. Remember, we talked about continuous distributions a while ago. The probability of being exactly on a score is 0. That's why we always have to find ranges. Okay? Because these are things that are measured. So, so we would say the probability of getting exactly k is 0. So we have to get the probability of being less than or equal to k. Or less than k. It doesn't make a difference with the equal. Okay, so what are you going to put in your calculator then?
0.9346 and
0.93, 46, and 25.
82.9.
That's all you retake.
Inverse norm.
Retake studies is
Okay? So, wait, what did you guys get?
82.9.
82.9, okay? So, if you got an 82.9 or higher, you're getting an A.
I want that.
Okay?
That's basically what we have, right? Just, like, take our curves.
Okay. Okay, one last one I want to go over here, and this one is kind of a challenging one, all right? We've got to find two different values, okay? Says the volume of cool drink in a bottle filled by a machine is normally distributed with a mean of 503 milliliters, standard deviation of 0.5 milliliters. 1% of the bottles are rejected because they're underfilled. 2% are rejected because they are overfilled. Otherwise, they're kept for retail. What range of volumes is in the bottles that are kept? I don't know if you've ever done this before, but if you look at like bottles of pop on the, or soda, on the thing, okay, up on the shelf, if you look at them closely, some of them are just a little bit more filled or a little bit less filled, but they're all within a particular range, you know. So that's what we're trying to find here. What's that range? Okay. All right, so for the 1% underfilled, we're doing inverse norm with 0.01, 503, and 0.5. And what'd you get, Anna? 501.8. Okay. And then 2% over, we're doing inverse norm. What's the area we have to use, or the probability? 0.98 with 503 and 0.5. Okay, and what do we get with that one?
504. Should we do safeties for the first one and make it 502?
Yeah, we can't. You can. Here's the thing: you'll never get docked for leaving more, but don't round it to 500. You know,
Right.
but if you left it as 501.8, that's fine. If you make it 502, since that's 3 sig figs, that is fine. Okay? So 502 to 504 would be acceptable here. Okay?
And then do we write like a greater than like 502 is less than and less than
What range of volumes? You could say something like that. You could say the volume is going to be between 504 and 502. That's fine.
But we don't have to do that?
Well, yeah, I mean, you should give some kind of an answer. Yeah.
And do we have to put units? Because I know it's...
Here's the thing with units of measure, all right? If everything in the problem is the same units of measure, I wouldn't bother, okay? Because if you accidentally put the wrong thing, you will get marked off. But you don't get marked off if you don't put any units of measure. The only time I would make sure to specify is if they ask for it, or if, like, we had a couple of different measurements and one was in milliliters and one was in liters or something like that, I would clarify what my answer was in. Okay? Now, one other type of problem I want to do here to tie together the last two lessons, all right? We've been looking at, let me give you the problem first, and then we'll address it, okay? Let's say, suppose 30% of, let's say, suppose 30% of, what do you guys want to look at?
Gatorade.
Gatorade, okay.
Children. Serial killer.
Has less than, let's say, it's a 1 liter bottle, so less than, let's say, 998 milliliters, okay? And let's suppose that 20% of the Gatorade bottles has over 1,001 milliliters. Okay? What's the average that a Gatorade bottle is filled? In other words, what is mu? And we're going to assume it's distributed normal. X is distributed normally with a mean and sigma squared. Okay? We don't. We don't know the mean or the standard deviation. All we know are these two percentages. And I'm giving you this, guys, because really this is about as complicated as these get. But even this is not terribly difficult. Okay? The key here is identifying if there is any situation where you don't know the mean or the standard deviation, you're going to have to use Z, the standard normal distribution. Okay? It is, but we're going to, so that means how many Z's are we going to have to find? 2. Okay? So standard normal, remember, standard normal has Z distributed normally with a mean of 0 and a variance of 1 squared. Standard deviation is 1. Okay? So, here's what we're going to do. I want to find the Z for that 30% that is below 998 milliliters.
Oh, I forgot you can use milliliters.
Yeah, okay, so here's what we're going to do. That Z is going to equal the inverse norm with a 0.3, a 0, and a 1. Okay? Well, standard normal is just another normal distribution. It just happens to have a mean of 0 and a standard deviation of 1. Okay? On the calculator, we're using inverse norm with the mean of 0 and standard deviation of 1. Okay? What do you get when you do this? Negative 0.524?
Yeah.
Okay. So that's the first Z. All right? However, I know that that corresponds to the score, the value of X, that is 998. Okay? So let's bring back to memory here. Z, what's the formula for Z? X minus the mean over standard deviation. Good. So guess what? I can write this equation with 998 minus the mean over the standard deviation. And now I have an equation. But it has two variables. So what do I need? Another equation. A system of equations. All right? So check this out. So now we're going to get the Z for the 20% below, or I should say above 1001. So yes, that means that we have 80% that is below 1001. Okay? So that Z is going to equal the inverse norm with not 1001, with a 0.8, 0, and 1. 0.842. Okay. So, again, using our formula for Z. Is everyone understanding what we've done so far?
Yeah.
Okay. Using our formula for Z, which is in your formula booklet in case you forget it. All right? X is 1001 minus mu over sigma is going to equal the 0.842. And now we have a system of equations that we can solve.
I'm confused. Do they sit next to each other now? Like, do they equal each other now?
Well, they're not equal to each other, but they both have a mu and they both have a sigma. So however you guys like to solve your systems of equations, like I would probably multiply by sigma. So I'd have 998 minus mu equals a negative 0.524 sigma. And on the second equation, if I multiplied that by sigma, I'd have 1001 minus mu equals a 0.842 sigma. And then I'd probably multiply the first equation by a negative 1. And that way, when I add it together, my mu's cancel out, and I have 3 equals 1.366 sigma.
So they don't equal each other? Like, how do they relate to each other?
They relate to each other because mu equals mu and sigma equals sigma. They have the same two variables. Okay? So my system of equations has two variables. So I multiplied this by sigma on both sides to get this. I multiplied this by sigma to get this. And now I'm just solving the system. Okay. Well, now now notice I used a linear combination to get rid of the mu's. So 3 equals 1.366 sigma, and what does sigma end up equaling then?
A number.
2.20. It's 2.196.
2.20196, okay.
2.20.
And now I can go back and plug that into any one of these equations. Let's say 1001 minus mu equals a 0.842 times 2.2. So I add the mu and subtract that other thing. At this point it's basic algebra. And what do we end up with? 990 something.